This is section 3.5. 3.5 is about vectors in 3 dimensions. What happens is 3.5 goes in and takes all of the ideas from 3.3 and combines them with the ideas of 3.4. Specifically, we'll talk all about 3-dimensional vectors. So you need to be really solid on the concepts from 3.3 before you attempt 3.5. Okay, so if you haven't already mastered those, you might want to head back to 3.3 and take another look at 3.3. Section 3.5, vectors in 3 dimensions. All right, let's start with what a vector is going to look like. A vector is going to go still from point A to point B, but now point A is A1, A2, A3, and point B is B1, B2, B3, because I have to have that Z value in there. A is still called the initial point, and B is still called the terminal point. The x component before was b1 minus a1, so that's not anything new. The y component was b2 minus a2, so again, nothing new there. But the z component, b3 minus a3, that's what's been thrown into this mix. That's pretty predictable, b3 minus a3 for the z component. Now, as far as addition and scalar multiplication, you may just want to look back at 2 dimensions and take a look at those. The concepts are exactly the same as far as addition and scalar multiplication. Vectors are now going to be in the form u1, u2, u3, because I have to have a z component there. So I'll have 3 values in the brackets. The length of u, or the norm of u, or the magnitude of u, whatever notation, whatever terminology you want to use, is going to equal the square root of u1 squared plus u2 squared plus u3 squared. Okay, so not just u1 squared plus u2 squared anymore. I've got to throw in u3 squared. Parallel vectors. If you remember, with 2 dimensions, vectors were parallel if u was equal to c times v, or if v was equal to c times u, or basically if one was just a multiple of the other. Okay, so for some non-zero scalar c, if one is equal to c times the other, they're parallel. If that c is a positive number, they're in the same direction. If the c is a negative number, they're in the opposite direction. Okay, so again, nothing new here. A unit vector. How long was a unit vector before? It was 1 unit long. It still is. Basic unit vectors. Now this is something that's ever so slightly different. Before, I was just 1, 0. And j was just 0, 1. But because I have 3 dimensions now, I have to include a 0 for the z value in each of those. And I'm going to need a 3rd unit vector. Now, do you think we could name it something creative like Fred or something? No. We named it k. So I, j, and k. And k is 0, 0, 1. They're called basic unit vectors because, first of all, they're unit vectors. They're the simplest ones we can get. And they're basic because they can form a base for all the others. All the others can be written in terms of them. So if u is the vector a, b, c, then u can be written as a times 1, 0, 0 plus b times 1, 0, 1, 0, 1, 0, and c times 0, 0, 1. So u is equal to ai plus bj plus ck. For example, because what we're going to do now is give you all the kinds of problems you've had before, just in terms of I, j, and k now. If u is 3i plus 4j, and v is 2j plus k, find u plus v. Okay, now just looking at u, I might have thought I was in 2 dimensions, but then v confirms that I'm in 3 because it has a k. All right, so to find u plus v, I could just treat it like an algebra problem. 3i plus 4j plus 2j plus k. Add your like terms, so I wind up adding 4j and 2j and getting 6j. I come up with the answer of 3i plus 6j plus k. Or if you don't like I, j, and k, you can convert it back to matrix form. So I have 3, 4, 0, because that was u. Then v was 2j plus k, so that was 0, 2, 1. Then add your corresponding entries, and I still get 3, 6, 1. So the coefficient of I is the x component. The coefficient of j is the y component. And the coefficient of k is the z component. All right, another example, this is going to seem familiar to you as well. Find a vector 6 units long in the same direction as v, which is 3i minus 4j plus k. Now you've seen this type of problem in section 3.3. And what I did in section 3.3 was I multiplied by 6 because I wanted it to be 6 units long, but I divided by the length of v because I wanted it to start out as 1 unit long. So I took however long v was, divided it by its own length to make it 1 unit long, multiplied it by 6 to make it 6 units long. So I'm going to multiply v by 6 over its own length. So 6 over square root of 3 squared plus negative 4 squared plus 1 squared. In other words, I'm going to multiply v by 6 over root 26. All right, next example. Let v be AB, where A is the point 3, 0, negative 1, and B is 4, 3, 5. If U is in the same direction as V, so they're parallel to each other, and the length of U is equal to half that of V, U is half as long as V, and U is QB, what is Q? That's what that's asking. Okay, so let's figure out what the heck they're saying, right? U is in the same direction as V. They're parallel, and U is half as long as V. Notice also that U and V end at the same point. That's really important. V goes from A to B. U goes from Q to B. And this statement about U being half as long as V, that is essential to this whole problem. All right, so we have A, we have B. Our vector goes from A to B. I want a vector that goes from Q to B, and QB is half that of AB. So all I did was I replaced U with QB, because we said U was QB, and I replaced V with AB in that circled statement from the previous screen. So what's Q? Do you see it yet? QB is half as long as AB. They both end at the same point. So what's that just a fancy way of asking you for? They're asking you for the midpoint of A and B. Q is just the midpoint of A and B. Okay, if you didn't see that, you might want to go back and look at that picture again. All right, so just plop it into the formula for midpoint. So 3 plus 4 over 2, 0 plus 3 over 2, negative 1 plus 5 over 2. And I got 7 halves, 3 halves, 2. So I just found the midpoint, but it asked it in such a way that they didn't just say, hey, find the midpoint. They had to make sure that I understood lengths and directions and parallel and all kinds of other concepts there. What if it had said instead, find M, so that MB is in the same direction as AB, but this time instead of half, it's a fourth? What if it had said that? I want MB in the same direction as AB. I want it to end at the same point. I want it to end at B, but I want it to be a quarter as long. We would find the midpoint twice, okay? Because luckily a quarter is, right, just half of a half. All right, so I have a point A, I have a point B. We want MB to be a quarter of AB. So I want it to end at the same point but be a quarter as long. I want it to go in the same direction too. So I already had the point Q from before. I found that already. But now I want M. And M is going to be the midpoint of QB. And you can see there, MB is a fourth as long as AB. And they can do other variations of this. They can say find AM, where that's 3/4 as long, or find MB, where that's 3/4 as long, or whatever. But you'll always find something about a half or a fourth, or they could even do an eighth, I guess. Probably won't go much farther than that, though. All right, we already found Q, which was 7 halves, 3 halves, 2. And now we want to find the midpoint of between Q and B. So just do the midpoint formula, but now use it with Q and B. So I'd do 7/2 plus 4 over 2, 3/2 plus 3 over 2, and then 2 plus 5 over 2. And I get that the midpoint of the midpoint was 15/4, 9/4, 7/2. So that is the M value. Okay, so that was section 3.5. As you saw, a lot of the same concepts that were in 3.3, but just with the Z component thrown in. Okay, so do a little practicing with 3.3 and 3.5. Those are really important sections for the rest of the semester.